All right, so this is going to be the last video for section 3.4. In this video, we'll go over examples of applying the second derivative test. So before I go into the examples, I just drew a picture to visually show what we're doing. And then you see the curve of the functions in green. And there's two extrema. There's a relative max and a relative min. So there's a relative max that occurs at C1. And if you notice the relative max, it's concave down. The shape of the graph is opening downward. So that means its second derivative is negative or less than 0. Also, there's a horizontal tangent line at C1, which means the first derivative of C1 is equal to 0. Now C2, it's a relative min, and the graph is opening up, so it's concave up, which means the second derivative at C2 is positive or greater than 0. And likewise, there's also a horizontal tangent line at C2, and that means its first derivative is equal to 0. So second derivative test is like the first derivative test. It's just a way of finding relative min or relative max. So the strategy, I'm going to first find the first and second derivatives. Then I'm going to find any critical numbers, specifically where the first derivative is 0. All right, I'm not going to focus on any critical numbers in which its first derivative doesn't exist. I'm specifically only focusing on the ones where its derivative is 0. After I get those critical numbers, I'm going to plug each of them into the second derivative. If the second derivative is positive or is greater than 0, that means the graph is concave up. And if it's concave up, like in our picture here, we have a relative min. If the second derivative at the critical number is less than 0, so if it's negative, it's concave down, which means there's going to be a relative max. Now, the third case, if its second derivative at C is equal to 0, the test fails, and you have to use the first derivative test to make any conclusive decisions. All right, after you determine it's a relative min or max, at that critical number, you're going to have to find the y value for that relative min or max. And that involves you have to plug in the critical number into the original function, f of x. All right, so that's the strategy I'm going to invoke. And here are two examples I'll do. So number 35 and 43 in our textbook. All right, so the first thing I need to do, I'm going to find the first and second derivatives. So f prime of x. So I use the power rule. X cubed becomes 3x squared. And then minus 3 times 2x. And then plus 0. All right, so the first derivative is 3x squared minus 2x. And I'll circle that. All right, so that's the first derivative. Now I find the derivative of the first derivative to get the second derivative. And actually I made a mistake, hold on. So we have minus 2x. That's supposed to be, because I have the minus 3 in front, it would be minus 3 times 2x, because I just focused it on x squared, derivative is 2x, but I still have the minus 3 in front, so it would be minus 3 times 2x, which makes that minus 6x. All right, so it's really 3x squared minus 6x is the first derivative. All right, and we know the last value 3 is a constant, so that derivative is 0 but for a constant. All right, so that's the first derivative. The second derivative, f double prime of x. So again, I'm doing power rules, so it'd be 3 times and then 2x, and then minus 6 times 1 because the derivative of x is 1. So the second derivative is 6x minus 6. All right, so those are the first, so there's the first derivative and second derivative. That's what I do for first step. So I just go ahead and find the derivatives. Now I'm going to find critical numbers. I'm specifically going to focus on the critical numbers in which the first derivative is 0. So where f prime of x equals 0. So I set the first derivative equal to 0. All right, so solving for x, I'm going to factor. So I could factor 3x, and that's going to make this become x minus 2. And so I have two cases. Case 1 is 3x equal to 0. And you divide both sides by 3, and you get x being 0. And in the second case, you have x minus 2. You add 2 to both sides, and you get x being 2. So I have two critical numbers, and they're 0 and 2. And I usually I'll use C1 for the first one being 0, and then C2 for the second one being 2. All right, now I'm going to determine are these relative min or max by plugging into the second derivative. And the second derivative was 6x minus 6. Okay, so the first one, when you plug 0 in, you get 6 times 0 minus 6, which gives you negative 6. Now the negative 6, the value itself doesn't matter, it's the sign. And since this is negative, we know the graph's going to be concave down. And if it's concave down, it's going to be a relative max. All right, so that max occurs at 0. So relative max at C1 equals 0. Now I plug in 2 to see if that's a relative min or max. So C2, the second critical number was 2. So it'll be 6 times 2 minus 6. All right, so that's 12 minus 6 is 6. And again, the value itself isn't what we're interested in. We just need to know if it's positive or negative. So this is positive. And since it's positive for the second derivative, that means it's concave up. So it's opening upward. That means there's going to be a relative min. That's at 2. So we're almost done. We've already determined, all right, there's a relative max at 0, there's a relative min at 2. Now I just need to find, well, what are the y coordinates that go with these? And remember to use the original function. And the original function was x cubed minus 3x squared plus 3. All right, so for the relative max, we said was at 0. I plug 0 into the original function. So it'll be 0 cubed minus 3 times 0 squared plus 3. All right, of course, those first two terms are 0, so you're left with 3. All right, so that's our output. The output's 3, our input is 0. That means the relative max is the point 0, 3. All right, last we just need to find the y coordinate that goes with the relative min. And the relative min occurred at our second critical number, which was 2. So plugging 2 into the original function would be 2 cubed minus 3 times 2 squared, and then plus 3. So when you calculate that, 2 cubed, that's 8. So really this will be 8 minus, and then 2 squared is 4, so minus 3 times 4 plus 3. All right, so that's going to give -1. And that's our output. Our input was 2. So the relative min is the point 2, -1. And that's the answer. We just needed to know what's the relative max and relative min. So quick recap. Let's go back to the beginning. So I found the first derivative, second derivative. Then I find any critical numbers by setting the first derivative equal to 0. And then I got 0 and 2 as the critical numbers. Then I need to determine if each one's a min or max. And that's when I plug the critical number into the second derivative. And the first one, we got -6, which is a negative number. So that means the graph's opening downward. And since it's opening downward, then it's going to be a relative max at C1 equals 0. And then the second one, we got +6. Since it's positive, that means the graph's opening upward, which means there's a relative min at C2 equals 2. And then the last thing we did was find the y coordinates that go with each relative min or max value. All right, and that's how you do the second derivative test. I'll make a comment. I guess an advantage for the second derivative test is that you don't have to find intervals of increasing and decreasing. So you don't have to find intervals of increasing and decreasing with the second derivative test. Right, so the first derivative test, you would have to do that, find the increasing, decreasing intervals. And that involves having to pick a test value from each interval. So to me, it seems more steps when you do the first derivative test. But they both give you same kind of results. It tells you what's the relative min or max. All right, so that's that problem. The next one, number 43. Again, we're going to apply the second derivative test. And before I do the problem, I'll make note that a relative min or max cannot be an endpoint of an interval. So they give us this domain 0 to 4 pi. So relative min or max can't be at an endpoint of a closed interval. Okay, so in other words, it has to be inside of 0 and 4 pi with open parentheses. All right, so that's an important distinction, is that you can have an absolute min or absolute max be an endpoint, but a relative min or relative max, you cannot have that be at the endpoints. So I figured I would say that, and now go ahead and work the problem out. So I find the first derivative. So you're gonna have to recall the derivative of cosine. That's negative sine x. So when we find the derivative of f of x, it would be f prime of x equals the derivative of cosine, negative sine x. And what's the derivative of x is 1, so that'd be minus 1. All right, that's the first derivative. Now the second derivative, f double prime of x, well, derivative of sine is cosine, so this will be negative cosine x and then plus 0 because the derivative of a constant is 0. So the second derivative is just negative cosine x. All right, so we've got the derivatives. Now I'm going to find any critical numbers. Now find critical numbers where the first derivative is 0. So we set the first derivative equal to 0. First derivative is negative sine x minus 1. And then solve for x. So I would add 1 to both sides. So you have negative sine x equal to 1. And then divide by negative. So that would be sine x equal to negative 1. So then I ask myself, well, when is sine negative 1? So what angles produce that? So this happens for angles theta equal to 3 pi over 2 plus any amount of revolutions beyond the first revolution around the unit circle. So it'll be 3 pi over 2 within 0 and 2 pi, and then any more revolutions, you do multiples of 2 in pi. So this is the general solution. So sine of theta equals -1 when theta is 3 pi over 2 plus 2 in pi. And I was going to write general solution. Now our interval is 0 to 4 pi, so we can narrow this down to a specific solution. So the specific solution for when sine of x equals -1 is when x is, so you obviously have 3 pi over 2, that's between 0 and 2 pi. And then when you go another revolution, 7 pi over 2 is between 0 and 4 pi. All right, so 3 pi over 2, that's between 0 and 2 pi. Then 7 pi over 2, that's contained within 0 and 4 pi, the second revolution that you go around. So you could also get the 7 pi over 2 by doing 3 pi over 2 plus 2 pi. And then you could write that as 3 pi over 2. And then 2 pi is 4 pi over 2. And so that's where the 7 pi over 2 comes from. You just go one more revolution around, which is 2 pi radians, and I just add that to the 3 pi over 2 to get the 7 pi over 2. All right, so I have these values. So my critical numbers, C1's 3 pi over 2, and then C2 7 pi over 2. All right, and this is the specific solution. All right, so now that I have these critical numbers, I need to plug these into the second derivative and apply a second derivative test. So now plug these into the second derivative. And the second derivative was negative cosine x. So plugging 3 pi over 2 into negative cosine x, that's negative cosine of 3 pi over 2. Well, 3 pi over 2 cosine is 0. So this would be negative 0, which is 0. Now notice we get 0. So when we get the second derivative equaling 0 for the critical number, so we get f double prime of c equaling 0, that means the test fails, right? So for the strategy in the third case C, if f double prime of c equals 0, the test fails, use first derivative test. So I'm going to note that it's going to fail in this case for 3 pi over 2. And then the same thing for 7 pi over 2. It's going to also fail. right? Because you get 0 again. Test fails for both critical numbers. All right, and when the test fails, we have to now go back to the first derivative test to make any conclusive answer. All right, so what we can say now is that the test is inconclusive based on the second derivative test. Now we got to backtrack and let's try the first derivative test to see, well, maybe it's still a min or max. We don't know with absolute certainty. So that's why we're going to use the first derivative test. So for the first derivative test, just hypothetically, so let's say we have this as our graph, and then this is C1, and then this is C2. Our first derivative test, you're going to have the critical numbers are the same. So the first derivative is 0 for each critical number. But then you'll notice that if it's a relative max, leading up to it on the left side of that max, the graph is increasing. And if it's increasing, that means the first derivative is positive. So f double prime of x is greater than 0. And then it goes from increasing to decreasing if it's a relative max. So this portion's decreasing. And that's first derivative is negative when it's decreasing. All right, and then for relative min, it goes from decreasing to increasing. All right, so this portion is increasing. All right, so what we're going to see is, all right, so we find our critical numbers. Okay, we've already done that. Then we need to determine intervals of increasing and decreasing. All right, and you do that by picking a test value in each interval. And then you're going to see, okay, if its test value is positive, if f prime of x is positive, then it's increasing on that particular interval. If it's negative, the graph is decreasing on that particular interval. Now, if it's 0, then the graph is linear. All right, after you determine these intervals of increasing, decreasing at the critical numbers, if it switches from increasing to decreasing, like in this picture, where we had C1 goes from increasing to decreasing, that means it's a relative max. Decreasing to increasing, relative min. Now, if it doesn't switch, then it's not a relative max or min. All right, that's what the first derivative test entails. Now I'm going to go back to the question. And again, we first tried the first or second derivative test. It didn't work. It's inconclusive. So now we're going to try, well, what happens when you apply the first derivative test and make our decision from there. And we already found our critical numbers, right? So the critical numbers, (3 pi over 2 and 7 pi over 2. The first derivative f prime of x, that was negative sine x minus 1. The original function f of x equals cosine x minus x, and they gave us the interval 0 to 4 pi. All right, so I like to visualize this as far as we're going to make the intervals. So form the intervals. And we don't use the endpoints 0 and 4 pi. It has to be in the open interval from 0 to 4 pi. So I'll go ahead and put parentheses. And we critical numbers, we got 3 pi over 2 and 7 pi over 2. So we have the following intervals. So we have the interval that goes from 0 to 3 pi over 2. And then we got the interval that goes between 3 pi over 2 and 7 pi over 2. And then last we have 7 pi over 2 to 4 pi. So I just got to pick some values that are in each of these test or intervals. So I picked some test values. All right, and I'll use orange for the color for the test values. And so the first test value between 0 and 3 pi over 2, you could just use pi. So x1 equals pi is going to be my test value. Between 3 pi over 2 and 7 pi over 2, I'll use 2 pi. And then last, between 7 pi over 2 and 4 pi, it's just some value I'll pick. It's 11 pi over 4. So those are my test values. I plug each of these into the derivative, first derivative. All right, so that's the process. All right, so the first one's pi. All right, that's my test value. So it's going to be negative sine of pi, then minus 1. Well, what is sine at pi? So that's going to be 0. So that'll be 0 minus 1. All right, so that's negative 1. Now, the point is that it's a negative derivative, so it's decreasing. So negative first derivative. That means the graph is decreasing, and that's on the first interval from 0 to 3 pi over 2. All right, so I know for the first interval, the graph is going down. Now I need to check for the other two. All right, so 2 pi, sine of 2 pi is also 0, so you're going to get the same case, 0 minus 1, which is negative 1. Again, negative first derivative. So that means it's going to be decreasing again. And that's the second interval that goes from 3 pi over 2 to 7 pi over 2. So the second interval is still decreasing. So it doesn't switch from decreasing to increasing or vice versa at 3 pi over 2. So that means 3 pi over 2 is not going to be a relative min or relative max. All right, now the third test value, that was 11 pi over 4. All right, so sine of 11 pi over 4 is negative square root of 2 over 2. So I'll have negative times negative square root of 2 over 2, then minus 1. A negative makes positive, so this is square root of 2 over 2 minus 1. And if you were to do that in your calculator, you'll get this to be a negative number. So since that's negative, it's decreasing on the last interval, 7 pi over 2 to 4 pi. All right, so it's decreasing on all the intervals. So since it doesn't switch from increasing to decreasing or vice versa, none of the critical numbers are relative min or relative max. So that's an important distinction. So we'll be in conclusion. Since the graph is always decreasing, then there's no switch from increasing to decreasing or vice versa. So decreasing, I'll do DC to increasing I and C, or vice versa. And that means none of the critical numbers are relative mins or relative max. So this means there are no relative min or relative max at our two critical numbers that we've had, 3 pi over 2 and 7 pi over 2. All right, so that's the answer. There's no relative min or max because we applied the first derivative test as our last resort. And from the first derivative test, we were able to see that the graph is always decreasing. All right, so that was just one I wanted to do that shows that the second derivative test can fail. And when it fails, to make any conclusive answer, you need to use the first derivative test. That gives you more confidence in saying that there is no relative min or max. All right, so that's it for this video, and that's it for this section. I'll be starting the next new section in the next video, but this was going over the second derivative test and then an example that worked and an example where it didn't work.